Hello, everyone. Welcome to the Engineering Product and Technical Program Manager Talks. A special welcome to TPM talkers, builders, doers. Welcome to the second part of a 16-part system design building block series where we aim to give you the essential building blocks that are critical to designing or developing any system. One example of a building block is a load balancer, which we'll probably use in every single design component in one way or the other. Load balancers are used to distribute incoming client requests among a pool of servers. It reduces loads, can bypass field servers, etc. So let's dive right in. We like to start with a thought of the day, and today's thought is from the prince himself, Machiavelli, who says the first method for estimating the intelligence of a ruler is to look at the men he has around him. The first method for estimating the intelligence of a ruler is to look at the men he has around him. Okay, now, what does this mean to you? Ping me below, like, subscribe, let me know what this thought means to you. For me, what this essentially says is for a technical program manager or an engineering leader or a product leader, this should essentially applies both ways. So the question I'd like to ask is what programs are you running and what programs are running you? I think a key skill as an engineering leader or as a technical program manager is that you have to work with people that are much smarter than yourself. So being humble, having that servant leadership mindset to be able to harness the best from them is a key. Inbox me for more discussion if you want to know how to do this. Another third question I'll typically ask is what teams are you building? What teams are building you? Okay, so who is this for? These series of talks are for technical program managers, TPMs, product TPMs, system engineering, engineering leads, essentially anyone that's involved in the tech ecosystem. And what are we going to cover in this system building blocks? We have already covered the domain name system, but also could look at load balancers in this session, databases, key value stores. But ultimately, at the end of the day, we'll look at all these other systems as well, content delivery networks, rate limiters, etc. Something I just want to point out is that, and this is not me, this is the Evening Standard, I've been pointing out that the United Kingdom, it's not alone, by the way, is at risk of having to fight for highly skilled workers in industries such as technology and banking. And the UK is among the top 5 countries to face a prevalent shortage of talent. Now, just to be clear, these talks are not just for the UK. This is actually for anyone really that wants to upskill themselves in terms of knowledge, because many of the building blocks that we'll discuss are also available for actual use in public clouds such as Amazon Web Services, Azure, Google Cloud Platform, etc. Okay, so now straight into it. What is load balancing? Well, millions of requests, right? Depending on what kind of system you have. Um, as part of the system design interviews framework series, we did an elementary design for the Twitter API where we estimated that at peak time, Twitter could be handling up to 1 million requests per second, right? So when you have millions of requests arriving per second in a typical data center, and my picture out of the way, and you have just say what thousands or hundreds of thousands of servers working together to serve those requests, you need a way to be able to distribute all those client requests in a way that you don't have a server that's hot or you don't kill a server over just because you reaches its limit. And for these kind of problems, a load balancer is the answer to that question, right? Because the job of the load balancer is to fairly divide all clients' requests among the pool of available servers. Load balancers perform this job to avoid overloading, crashing servers, overloading or crashing servers. Um, the LB or load balancing layer is the first point of contact with a data center after the firewall. It could be required if a service entertains, from 100,000 requests and above. So let's look at a simplified workflow of a load balancer, right? So that's a load balancer. Essentially, it sits in between the client and servers. There are multiple places that a load balancer can sit, just to be clear. This example is just between clients and servers. Now, if you look at it, right, how does a load balancer help with scalability? When you add servers, okay, the capacity of the application or service can be seamlessly increased, okay? But load balancers help make such upscaling possible or even downscaling. And they also make it transparent to the users, availability as well. If some servers fall over, keel over, or suffer a fault, which does happen, the system will remain available. One of the jobs of a load balancer is to hide faults and failures of servers. And in terms of performance, how does a load balancer help with performance? When they forward requests to servers with lesser load, right? So imagine server one is too busy, load balancer puts it to server two, and I'll discuss some of the algorithms you use to do that later, or sends it to server three. Then it helps with performance because it takes away some of the load from the server. Generally, load balancers will sit between a client and a server. Requests will go through to servers and back to the clients through the load balancer or through the load balancing layer. Sometimes you can have multiple load balancers depending on your system. Let's consider three well-known groups of servers. Okay, these are the web servers here, application servers here, database servers here, right? To divide the traffic load among these three different types of servers, we can use load balancers between the client and the web server. We can use load balancers between the web servers and the application servers. We can use load balancers between application servers and um, database servers. Now, this is the typical three-tier structure. Okay. Let me know below if you think there are other ways that load balancers can be applied, or if you want something else that you feel is not covered here. Okay. So generally, load balancers enable services to be scalable, available, and highly performant, as I just said. They also offer some other key services like health checking. So they can use the heartbreak protocol, the heartbeat, heartbreak, the heartbeat protocol to help you monitor. So like a regular ping, and then if nothing comes, it pings the server, pings the server. If there's no response, you know something is wrong after a set period of time. Um, Load balancers can also help predict, can help with TLS termination. So they can reduce the burden on end servers by handling TLS termination with the client. Okay, they can help in predictive analytics because they can predict traffic patterns because they capture this history by performing analytics on traffic that's passing through them, or they can use statistics of traffic that has been obtained over time. Load balancers help with service discovery. One advantage of load balancers is that client requests are forwarded to appropriate hosting servers by inquiring about the service registry. So they have that information. Security, load balancers can help with security because they can mitigate attacks like denial of services at different layers of the OSI model. So think of layers 3, 4, and 7. As a whole, just in terms of summary, load balancers, they provide flexibility, reliability, redundancy, and efficiency to the overall design. Now, someone can say, what if load balancers fail, right? Don't they become a single point of failure? Um, the way this is normally dealt with in reality, certainly the way I've seen it being dealt with, is that you don't deploy a single load balancer either, right? So typically deployed in pairs so that for disaster recovery or DR, if one LB or load balancer fails, then you can easily fail over to the secondary load balancer. Um, to maintain high availability, what I've seen enterprises do is that they actually have clusters of load balancers. So several that use a hybrid communication to communicate to each other and to check their health. So if there's a failure of the primary load balancer, the backup can take over. But if the entire cluster fails, manual rerouting can also be performed, right? So if there's that kind of emergency, then you can use manual rerouting. Now, I think a logical question would be how how would this be performed, right? So there are different algorithms, right, to route client requests. Some of the well-known algorithms are sort of round robin, where each request is forwarded to a server in the pool. Just think of it like what we see in the Premiership, round robin league. There's a weighted round robin. It's essentially a round robin, but a weight is applied to each node based on different factors. So therefore, the higher the weight, the higher the number of assignments to that um, node. There's also the least connections algorithm. So in these kind of situations, even if all the servers have the same capacity to serve clients, uneven load on certain servers could still happen, could still occur, it's still a possibility. So, for example, some clients may have a request that requires longer to serve. So you can't just differentiate by the number of requests since the time on task could be longer. Or some clients could have subsequent requests on the same server or the same connection. So in that case, we can use algorithms like the least connection, which will check the number of connections that the server has, and then it will assign to servers with the fewest. Is that correct? Fewest, yeah, fewer. The fewest is the word. With the least, with the least connections. The load balancers in this case will keep uh, um, a state of the number and the mapping of those connections in such a scenario. I'll talk about state maintenance later in this talk. But for least response time, which is another way, or which is another algorithm, um, for performance sensitive services, algorithms such as least response could be used. What this algorithm does is that it ensures that the server with the least response time is requested to serve the clients. Something else is IP hash, right? So that's Internet Protocol hash. Some applications provide let's say, various levels of service based on the IP addresses. And in that case, you can hash the IP address and then use that to assign users requests to servers. There's also an algorithm called URL hash, which is within some applications, right? The the services within those applications will be provided by specific servers alone. And in that kind of situation, then a client requesting service from a specific URL will be assigned to a certain cluster or set of servers. In that kind of situation where a client is assigned to the specific server, then you want to use the URL hash algorithm to identify whether those services, those connections are too many or too few. What this essentially says is that there are stateful algorithms or stateful load balancers or load balancing service systems and stateless load balancing. And these are essentially the two ways of handling session maintenance through load balancers. Okay. So for stateful load balancers, just as the name implies, it involves maintaining a state of the sessions that have been established between clients and hosting servers. The state Full load balancer incorporates, state information in the algorithm to perform load balancing. So a data structure will have to be retained. This data structure will map incoming clients to the hosting servers. Stateful load balancers, I must say, they increase complexity and limit scalability because the session information has to be retained. So you can see the script. You can see this. So these are your clients on the left. These are the different sessions. And you can see for each of the servers, application server, right? Right. So for each of the servers here, right? So for each of the servers, application server, you see that it has to store the session information, right? So the session information is stored. That's something about stateful load balancing. Then for stateless load balancing, it does not maintain any end state. It does not maintain any state information. Therefore, it's typically faster and lightweight because there's not that additional complexity or overhead of trying to store, trying to remember what happened, what happened, what happened. It doesn't have to store the state. Therefore, a state maintained across different load balancers will be considered as stateful load balancing, but a state that is not maintained will be assumed as stateless load balancing. Okay. So depending on requirements, load balancing can be performed at the network or transport and application layer of the open system on the Open System Interconnect, right? So that's OSI stands for the Open System Interconnection Layers. So at layer 4 load balancers, layer 4 refers to the load balancing that is performed on the basis of transport protocols like TCP and UDP. TCP is standing for Transmission Control Protocol, UDP is standing for User Datagram Protocol. I just discussed about it previously. Now, these types of load balancers, they maintain a connection session with the clients and they ensure that the same communication ends up being forwarded to the same backend server. So even though TLS termination is performed at layer 7, some layer 4 load balancers support that. There are also layer 7 load balancers. These are those load balancers that work based on the data of the application layer protocols. Okay, so here you can make application aware forwarding decisions based on HTTP headers, URLs, cookies, and other application specific data. For example, the user ID. Apart from performing TLS termination, such load balancers can take responsibilities like rate limiting users, HTTP routing, and header rewriting. Yeah. There's also different ways in which load balancers can be deployed, right? Across 4 tiers, tier 0, tier 1, tier 2, tier 3. Um, yeah. So if you imagine a 3-tier load balancer in a typical data center, you have clients, you have your server. So tier 1 would be the router, right? So equal cost multipath, ECMP stands for equal cost multipath routers. These are tier 1 load balancers. From the name, it's evident that what this layer does is that it divides incoming traffic on the basis of IP or some other algorithm like round robin or weighted round robin. Tier 1 load balancers will typically balance the load across different paths to higher tiers of load balancers. Then tier 2 load balancers, yeah, these typically include the layer 4 load balancers that we just talked about. They make sure that for any communication, incoming packets are forwarded to the same tier 3 load balancer, right? So remember, it's a hierarchy. And to achieve this goal, a technique like consistent hashing, right? So consistent hashing, I will talk about that, can be used. Um, Something here is that if there's any change to the infrastructure, consistent hashing may not do. Therefore, even with this, you may need to maintain a local or global state. Tier 3 load balancers, these are layer 7 load balancers that provide services at, so layer 7, application data layer 7 load balancers that provide load balance at tier 3 level. And essentially, what happens here is that they perform health monitoring at this level. This tier also enables scalability because it distributes requests across the set of healthy backend servers and provides high availability by monitoring the health of the servers directly. Something else is that, to summarize, let's just summarize, right? So to summarize, tier one balances the load among the load balancers themselves. Tier 2 um, enables a smooth transition from tier 1 to tier 3 in case of failures. And tier 3 does the actual load balancing between backend servers. Yeah. The expectation is that each tier performs tasks to reduce the burden on end servers. Now, the other types of load balancers, just want to quickly bring to your attention. There are hardware load balancers. These were introduced in the 1990s as hardware devices. They work as standalone, right? So they work as standalone devices. They're quite expensive. They have their performance benefits, and they're able to handle a large number of concurrent users. Configuration of hardware-based solutions is problematic just because it requires additional human resources. Therefore, they're not typically the go-to solutions. They're expensive, standalone. Now, there's software load balancers, which are becoming de facto industry standard just because they're flexible, programmatic, and they're cost-effective. And this really is because they're implemented on commodity hardware. Then there are also software load balancers. Sorry, they're also cloud load balancers. And these ones essentially drive load balancer as a service, or LBAS. And the primary advantage of cloud load balancers is that they're easy to use, management straightforward, um, they are metered. In other words, if you're not using, you don't pay for what you don't need. Essentially, all the principles that have made cloud so popular. That's essentially how these load balancers work. Okay. So just to recap, we have looked at load balancers previously in the previous session. We looked at domain name system. Now we have looked at load balancers. We've looked at the hierarchy, the different tiers, the algorithms that determine how load balancing is done. We've explained why load balancing is important, what the system entails. In our next session, we'll look at databases. If you have any comments, don't forget to like, subscribe, click below. Let me know. Thank you. I will see you on the next one.